Bismillahirrahmanirrahim. Assalamu alaikum and good morning to all students. And welcome to 9618 AS class. In our previous lecture, we discussed binary arithmetic. We discussed how we can add binary numbers together, how we can subtract them, how we can use one's complement and two's complement to represent the signed numbers, and how we can use the two's complement method to add values in binary. And also we discussed the benefits of two's complement over the sign magnitude method. And I'm sure you have gone through the worksheet as well. In our today's topic, we are going to learn how the text is represented in computers. The first numeric coding scheme which I'm going to discuss is binary coded decimal. First of all, we are going to discuss this numeric coding scheme, then we are going to discuss an alphanumeric coding scheme, ASCII, and then Unicode. Now, in BCD, each number is represented by a group of 4-bit binary. You might remember that the largest binary digit is 9, and 9 can be represented in 4 bits. So, we use 4 bits to represent each denary digit in BCD. This 4-bit conversion is actually just as same that you learned in the first lecture of hexadecimal conversion to binary number system. But this time we are going to call it denary. Now let's see an example. A decimal number system 4926 can be represented in the binary coded decimal in groups of 4 bits, 4 bits dedicated to each digit. And if I do that, the 8421 BCD, 8421 is the coding scheme number of BCD, would be represented such as this. The 4 is 100 and a 0 is added to complete the 4 bits. 9 already has its 4 bits completed, and 2 is 10, so 2 zeros are added to the left, and 6 is 110, so a 0 is added to the left to complete the 4 bits. So the idea in the BCD is to represent each digit in the groups of 4 bits. Then let's talk in reverse. Let's talk about converting a BCD number into decimal. Again, we are going to follow the same rules. As you can see, the BCD number is 3 groups, and in each group you have 4 bits. So we are just going to convert them. And you might remember the conversion method. There was a longer conversion method and there was a shorter one. In the short one, you can just write the solution of the powers of 2 on top of each digit, and then you can just add the ones and you have your conversion. So when you convert it, it is going to become 871 in the denary or decimal number system. Remember, we are using the 4-bit conversion method, but we are actually going to decimal number system. The conversion method may seem the same as hexadecimal, but it is the binary coded decimal that we're talking about. BCD coding scheme is largely used in digital electronics. Maybe your calculator display is using the BCD coding scheme. Maybe your other electronics items or electrical equipment is using the BCD coding scheme to do the calculation and to display the characters. How actually BCD performs the addition is another thing we need to understand. Let's consider this example. We have a BCD representation of 0.26, and you can see that this is your integer part, where since it is only 0, so both the nibbles are 0. Nibble is a group of 4 bits, and these 4 bits are representing 2, and these 4 bits are representing 6. I have already told you that binary point doesn't exist in computer. We just convert the integer and the fraction separately, and we store that in separate areas. So this area is reserved for my fractional part, and this area is reserved for my integer part. Now I'm going to actually add this with this value 0.85. Again, the integer part is 0, so it's all zeros. And then we have 8 and 5 represented as a 4 bits. Now we already studied the binary addition in our previous lecture. So let's go ahead and try to do that. So this 0 and 1 is going to be 1. This 1 and 0 is going to be 1. This 1 is going to be 2. So binary of 2 is 1 0. We are going to write the 0 here, and we are going to carry the 1 here. So this one added to these two zeros is 1. Okay, good. Now these two zeros, 0 and 0 is 0, 1 and 0 is 1, 0 0 is 0, and 0 1 is 1. So that's it, I think. But the problem here is, if I add these here in the denary number system, if I add them, 5 and 6 should be 11. So 1 is here and 1 carry, and 3 and 8 should also be 11. So 1 here and 1 carry. So it should be 1.11. But when I'm looking at these digits, they are far above 9. You can easily see that this is your 11. And we don't have any digit named as 11 in the decimal number system. The largest digit that should be there is 9. And this digit has become 10. And we don't have a digit named 10 in decimal number system. The largest digit we can have is 9. So that means there has been an error in the addition of the binary coded decimal number system. Now, this coding scheme has a solution for this as well. Whenever you have something which is greater than 9 as a result of an addition, that means an error has occurred. And if the error has occurred, we have a mechanism to correct that. Let's see how we can do this. I'm going to write all that values again. And this is the answer. This right here is the answer that I had in my previous slide. What I'm going to do is I'm going to add a special nibble, a special group of 4 bits, which I'm going to call the check nibble or the correction nibble to the first nibble of my answer. This 0110 acts as the correction nibble, and if this sort of error occurs, we are going to add this to the value in order to correct it. So I'm going to add this correction nibble to this first nibble of my value. I have what I'm going to get is 0 plus 1 is 1 and 1 plus 1 is 2. So 0 here and 1 carry forward, and 1 plus 1 is again 2. So 0 here and 1 carry forward, and 1 plus 1 is again 2. So 0 here and 1 is carried forward to the next nibble. Now this was actually the problem. In this addition that we did in the previous slide, the problem is that the carry 1 was not being forwarded to the next nibble. Now we have the carry forward and we are going to again add the correction nibble to the next nibble. Now this one. But remember to add the carry as well. So this 0 and this carry 1 and this 0, all of these are going to be added. The answer is going to actually be this. So 0, 1 and 0 is 1. This 1 and this 1 is 2. So you have a 0 and 1 is carried forward here. This one and this one is again 0 and 1 is carried forward here. And this one and this one is again 2. So we are going to write a 0 and we are going to carry a 1 forward. Now you can see that this one has been forwarded to the next nibble. If I write the answer of, this was the answer of my first addition of correction nibble, this was the answer of my second one, and this is the answer of my third one. So combining all these answers, I have the correct answer, the answer that should be there. So I hope you understand how the binary coded decimal coding scheme works and how the addition of BCD works and when to add the correction nibble. Whenever we are having a value which cannot exist in the BCD, any digit larger than 9, we have to add correction nibble into that addition separately. Each digit is corrected separately and then we have our answer. Moving ahead, we have the ASCII code. You have already been introduced to ASCII coding scheme in your O levels. As you know that it stands for American Standard Code for Information Interchange. It was actually developed by ANSI, American National Standard Institute, to represent the English character. So ASCII basically mostly represents the English text. If you see the ASCII character code table, you can see that it has the decimal representation, the binary representation, and the English character code that you are familiar with. So by using this table, we are able to represent each character in terms of numeric values, and then those numeric values can be converted into binary and then they can be stored inside the computer's memory. ASCII stores the English language uppercase and lowercase characters and the punctuation marks and the digits and some special characters as well. Uh, the characters that tells the computer where there is a tab or where is an enter key is pressed or the end of line characters you might say. These are all represented in ASCII and you can call these non-printing characters, or when the telex or telegraph was used. They are control characters to show the start and end of the message. They are represented in ASCII. The first 31 characters have been allocated to them. And as I was telling you, they assist in data transmission and the handling of data at a computer terminal. By data handling, as I was mentioning, where there is an enter key or a tab key is pressed, a special character is added to tell the computer that there has been an end of line character. So that end of line character has to be represented with a character code. Although it's a non-printing character, it doesn't show, but still it's there. So character like these are represented in ASCII as well. Then ASCII is mostly for English language. All the characters you find in ASCII are the standard character you find on your keyboard as well. ASCII also includes the characters in a sequence. Means if you have a character, for example, if I had 65A, so I can just add and I will get the 66, which is the character code of capital B. There is one more trick to ASCII as well, that each uppercase and lowercase character code only differs in the bit 5. For example, if I have the capital A's code 65 and it is represented like this, I can just flip the fifth bit to 1 and I can have the character code of small a. There is a sign of equality missing here. Don't let it confuse you. So let me just show you the table again too. Yeah. So for example, I have the character code of B66 and this is the binary of B. Okay. Let's compare it with the binary of the lowercase b. You can see most of the binary representation is just the same. Just here in the bit 5, we have flipped the 0 to 1. You can convert 66 and 98 and see that this is true. This is just a trick to quickly switch to uppercase to lowercase or from lowercase to uppercase. In the uppercase, this bit 5 is always going to be 0. As you can see from A to Z, this bit 5 is always 0. And in lowercase, the rest of the bits are same, but this bit 5 is 1. So this brings to the problem. This brings us to the problem that ASCII is able to represent the English characters, but what about other languages like Urdu or Chinese or Japanese or the languages that are not using the Latin alphabets? For that, we actually came up with another coding scheme called the Unicode. The Universal Coding Scheme, a worldwide coding standard, is actually having a bigger coding space than ASCII. In a 7-bit ASCII, we were able to represent 128 characters. In 8-bit ASCII, we are able to represent 256 characters. But Unicode has much more capability of representing the characters. We have bigger coding scheme in Unicode. Unicode coding scheme have different versions as well. These versions actually just tell you how many bits we are using. So this is how we actually write a code point in Unicode. But Unicode U-8 and U-16 and U-32 actually just the versions of Unicode. This U-32 actually just mean that you're using a 32-bit Unicode and your coding space actually increases. These are some reasons that actually forced the invention of Unicode. This is actually different versions of Unicode. You don't have to actually memorize this table. This is just for your knowledge. This is not even directly part of your syllabus. This is just to show you how the Unicode actually, uh, the variety of Unicode which is the Unicode is having. The UTF-16 and the UTF-8 is mostly what you encounter in your text handling. The one character representation in Unicode is called a code point. So the largest and smallest code points are represented in these columns. The code unit size here is 8 bits. The code unit size here is 16 bits. The rest is also there for you to explore and go through. The fewest byte size per character is 1 here. And the least number of bytes you can use in UTF, you can be using in UTF-16 is 2. The max you can use is 4. And there's a link which I'm going to share with you in this Zoom group as well. And in this link, you can see that there are a lot of, excuse me, yeah, there are a lot of different information which is provided about the Unicode. So please go through it to have a much deeper understanding of this coding scheme. The differences between the Unicode and ASCII is ASCII had the 7-bit ASCII, or you can call it the US ASCII as well, has 128 codes, 2 raised to power 7, and Unicode has a bigger coding space. ASCII is mostly using only English language. Unicode can accommodate other languages as well. There are some similarities as well. They both are character codes, and the first 128 code positions of Unicode actually same as ASCII. Means you can say that ASCII is included in Unicode. ASCII is a subset of Unicode. Unicode has the capability of representing uh, English language characters as well as other languages as well. That's all for today's lecture. I'm hoping that you have gone through the worksheet that have been previously shared. Uh, you can send it back to me through email, and I will give you the feedback individually on that. Stay safe. Allah Hafiz.